Okay, so now we'll start with the last part of the thermochemistry, and we'll talk about that is known as the collision reaction theory. In order for a reaction to occur, there are three conditions that must be met. The reactant molecule must be collide between each other. The collision must happen so that the reactant collide within the right orientation. And the reactant must collide with enough energy that they actually react. This is known as the activation energy. Okay, so what is happening here is we see a collision that is happening, and then as a result of this, it is products are formed. Okay, so now what do we have to keep in mind? During bond formation, the energy is released, and during when the bonds are broken in a chemical bond, then the energy is required, is absorbed. The change in enthalpy, as we have said, the change in enthalpy of a reaction represent the net effect from breaking the bonds in the reactants and forming the bonds in the product. In the exothermic reaction, bond breaking absorbs less energy than bond forming gives off. So that will result into a negative delta H. An example of this is when we have hydrogen and chlorine that are forming chloric acid, plus energy. So what do you see here in terms of the kinetic energy is that here is a reaction process. Is that they start somewhere here. And then they go somehow up, and they come down here. Okay, so they go up and then they go down. In an endothermic reaction, bonds breaking absorbs more energy than the bond formation gives off, resulting into a delta H positive. So when we have, so this was an exothermic reaction, and what is happening in an endothermic reaction is that here is the reaction process. So they will start here somewhere, and then they will go some up, and will form whatever. So this is an example of this is, let's say, breaking water. Two, and then balanced one will be 2, 2, with liquid, gas. So the graph will look like this. The energy barrier must be overcome for a chemical reaction to occur. It's called that must be overcome. It's called activation energy. It's called activation energy. The atoms in the reactants have to be pulled apart in order for them to bond in different configuration and become the products. Okay, so the atoms in the reactant has to be pulled apart, same as what is happening here in this picture here, and then they are collided and they are forming two more products. The activation energy is always higher than the energy contained in the reactants and in the product. However, the amount of energy activation energy necessary depends on the reaction. The top of activation energy, so this is net change. So this is where it starts. This is the activation energy, and this is net change. Final, initial, final, initial. Okay, so this is what is happening in an endothermic reaction. This is what we have in an endothermic reaction. This is what we have in an exothermic reaction. Okay. Catalysts are substances that are added in order to lower the activation energy. So instead of having an activation of energy that has a high spike, we add catalysts to lower that activation energy, to easily break the bonds on the reactants to give them the opportunity to form products. They are not classified as a reactant or product. They are just present there because they just help to make the activation energy lower, but they don't, they are like, they are as a spectator in the reaction. If the activation energy is lower than more molecules will have enough energy to react. And a catalyst, as I said, they do not affect on the enthalpy change because they are spectator, they do nothing. If we have an uncatalyzed reaction happening, the spike of the activation energy is higher than when we have an catalyzed reaction happening. And what do you have to keep in mind at the very end is that what is final and what is initial. That is what is important in the reaction. So if we have, let's suppose that we have water and fluorine acting together or reacting together to form hydrogen fluoride, then if we have like no catalysis added into the reaction, then the spike of the energy is way higher than when we have a catalyzed path. But what is important all the time, no matter what, with activated energy without or with catalysis on it, then always the enthalpy change of formation for hydrogen fluoride will be negative 546.6 kilojoules. And this is pretty much what they are saying here. The same thing is here. It doesn't really matter what is the activated energy, if there is or not a catalyst or not on it, then always we have to look for the final and for the initial. So just keep in mind when we have when we are expressing the energy into the graph, what we did before, it was just this is the product and this is the reactant. But now, in order to have when we are expressing it in terms of the activated energy, then we will have a spike. And if it is a catalyst participating in the reaction, then the spike will be not as high as without a catalyst. Well, that's it for thermochemistry. I will do a review later on, or we can do it in class. Depends on what we have to, how the day will go with us, and then that's it for thermochemistry.